Hello everyone, my name is Kabaga Jeanette. I'm very excited together with my group members to present to you our project GAN-Augmented Multimodal AI for health meal preparation and local food sovereignty. My group members, Nagunya Desire Christina Seku Jovan, our project mainly focuses on local meal preparation and in coordination with maintaining someone's health. So using the available local ingredients that we have in our country, we can be able to prepare a meal that is healthy and very affordable using affordable ingredients instead of depending on Western foods and ingredients, which may sometimes be very expensive and not even healthy. So we are mainly trying to create something that is very affordable to everyone that is in the country and mainly concerning food. To talk about these keywords in detail, let's begin with the multimodaling. Multimodaling is like simply using multiple types of data together, for example, text, images, and videos, so that AI can understand information more completely. So in our case, we use the recipe text, the food images, and some videos to combine and help us build the model to recognize what is being cooked and the ingredients used, and the steps taken to cook this type of food. If we're moving on to the GAN-based data augmentation, we use the GAN models to create new realistic data because our data set was so small. So we needed to increase the number of images so that the training process can become easier because it was failing due to little data. Our next key concept is computer vision, which allows the system to see and identify ingredients from images. For example, if your camera is pointed to a plate of food that contain matoke, beans, or kosho, you can be able to identify that this is beans they used matoke, they used kosho. And then if you have to move on to the large language models, these ones work with the text parts, so they read and understand the recipes and they give you like instructions step by step on how to do the cooking. And then lastly, we look at the knowledge graphs. The knowledge graphs organize information like ingredients, nutrients, and health recommendations. They help the system to suggest healthy meals for someone who's undertaking like health goals. If they are sick and like they need based on eating, they're able to recommend food that is aligning with their goals. Before building our system, we looked at several research papers and models related to food recognition, GANs, and multimodal AI. For example, we said how to train vision transformers for improved food classification and how clipping text and images, and also how the food knowledge graphs use knowledge graphs for nutrition recommendations. However, most of these models are based on Western cuisine, so we're finding difficulty on how to get data that is almost related to African meals. So but we use that information to be able to design, and it helps us as we design our system. Now, if we look at the problem statement, there are two main problems. There is the domain application problem and the computation problem. The domain application problem is that most food or recipe apps today are biased because they are based mainly on Western recipes. So it's hard for Ugandan users to find health local recipes based on the ingredients they actually have around them. So they have to continue sourcing ingredients that are processed outside but not locally what they have. Our computational problem, on the technical side, there's not enough data about the Ugandan foods online. So there are very few recipe descriptions, not even the images that detail what you actually want. So also, integrating multiple AIs like computer vision, the large language models, and the GAN in one system is very complex. So, even lastly, like most people don't have like high-end devices that we need for this model to actually run efficiently on a phone. So it's not like locally. To solve the above problems, we set up four main objectives: to build a multimodal AI assistant combining both computer vision and nutrition knowledge graphs, based on the Ugandan food ingredients that we have. To also implement the GAN to increase our data set. To also use the computer vision to be able to recognize ingredients and portions in real time. Also to deploy that model on offline mobile apps so that they can perform well with limited resources. So from these objectives, ask ourselves questions like what models can effectively integrate this scalable multimodal kitchen assistant, or how effective can GAN-based data increase the visual data set that we have, and also what features can be derived from the computer vision that are most reliable for real-time cooking validation and automated input estimation. Looking into our Ugandan food data set, there was no ready-made data set for these foods, so we had to create our own food. We used data from traditional cookbooks. One of them was a cookbook of Ugandan traditional foods, which contains authentic recipes. Then we scraped some from over like 60 PDFs, and also we got food images from over the internet to make the to make the data set richer. In total, we collected over 1,000 images representing 40 food categories, and also we created 162 recipe files in JSON format to describe the ingredients, cooking steps, and the names of the food, both in local and English language. We performed an EDA on our data set, and we realized that there's some corrupted files in our data. So we did some cleaning, and at the end of the cleaning, we were able to only get 978 images that were valid, and also ensure there are no corrupted files. So we also checked the distribution of classes to ensure that each class type had enough samples. The EDA showed that the local foods have a diverse texture and color, which may be difficult for visual recognition, but it's very interesting for our model to learn from. The samples of the images from our data set were taken under different lighting and background. Some were from the kitchen, and others were like from the kitchen places. So this diversity also enables our model to generalize better and learn because it's able to recognize foods taken from different conditions. Looking at our methodology and system architecture, our system architecture brings together four main major AI components. A vision transformer, the VIT for recognizing ingredients from images, a rational graph conventional network that empowers the nutrition knowledge graph. Then we also look at the fine-tuned large language model that processes and processes text, ingredients, and processes. There's the clip model that connects the images and the text in the same understanding space or working space. These components communicate with each other so that they can be able to complete our model. For example, the vision model can recognize food from images. When a user inputs an image, the vision model recognizes and identifies that type of food, and so that then the large language model can fetch the recipe for that food. Then the knowledge graph is able to suggest the healthiest way to prepare that food, or look for which nutrients that the user, if they are on a health plan, that will be good for making that type of food. Let's look at the model architecture and the mathematical foundations of the models. So model 1, the RGCN knowledge nutrition graph. So the RGCN is the mathematical core of our knowledge graph model. It represents nodes and relationships. It represents data as nodes and relationships. So the model learns a vector representation of each node. This vector representation capture the meaning and the connection of the node in the graph. So to do this, they use a mathematical formula, and that is like the formula 1 that is written there. So the goal is to make similar or related nodes closer together in a vector space. To measure the plausibility score, we use the distill-mouth scoring function to do that. So this means that the model multiplies the vector representation of the head, the relation, and the tail. For example, beans contains proteins, and then it adds them up and gets the results. The higher the score means the relationship is most likely to be true. The model uses the Bayesian personalized ranking laws, which encourages the model to give true triplets of higher scores than the false ones. In simple terms, the RGCN learns to understand the structure of the food nutrition world mathematically, helping the system to make health-aware meal recommendations. Next is the fine-tuned large language model architecture and mathematics foundations. So, in this model mainly handles all text-based understanding. It converts words into mathematical vectors, processes them through neural network layers. So we're going to look at each of these neural network layers. We're going to begin with the embedding layer. So in the embedding layer, each word is mapped onto a numeric vector, and this process is called embedding. So it uses a mathematical equation. So this equation makes sure that the model transforms words like matoke or beans or posho into vectors that can capture meaning behind the words or even the context of those words. So from the embedding layer, we move to the linear transformation. This is where the model learns patterns by combining features using an equation. So the variables in these equations are like learnable parameters that help the model identify relationship between the words. So from the linear transformation, we move to the LU activation. So after the transformation, the LELU function keeps positive information and removes the negative noise. So after the RELU activation, we move to the patch normalization and dropout. So this stabilizes the learning process by preventing overfitting, meaning the model does not just have to memorize one recipe, it memorizes like a number of recipes. After that, we move to the softmax layer. So at the output, the softmax layer converts raw scores into probabilities. So it can predict that the probability, like if it's a recipe, that the probability, let's say it's a recipe of some food and you're cooking the next step, it can predict that there's a high probability that the next step is going to be like steering. So it will be like the probability of the word that comes next is going to be steer is 90%. After then, we move to the loss function. Here we use the cross entropy loss to calculate how far these predictions are far from the correct answers, so that to increase accuracy of the model. Then we move to the optimization. Finally, the model adjusts its parameters using the Adam algorithm, which adapts the learning rate to make the training faster and more stable. So altogether, these steps mathematically describe how large language models reads, understands, and generates like cooking instructions for the system. Finally, the VIT model. This one interprets images of food. So how it does it, like instead of scanning small pixels like the CNNs, it divides an image into patches and treats each part like a word in a sentence. So suppose like an image of 224 times 224 pixels, this model will divide it into smaller patches, like let's say 16 times 16 pixels. So to give us several patches. So using mathematical equation, it turns them into vectors. So with this mathematical equation that's given, like how you see that part that has the input. So the piece is the patch size and sees the number of color channels. So they are usually like 3, like the primary colors, red, green, and blue. So then when these patches are put into the embedding space, they are put there using a formula. Z naught equals XP plus WE plus BE. So with that, a special token is added to represent the whole image. So after this token has been added to represent the whole image, positional codings are added so that the model knows where each part is located in the image. This sequence passes through multiple transform encoder layers, and these layers contain each a multi-head self-attention, a feed-forward network, and a layer normalization and extension networks. The multi-head self-attention is where the model compares each patch with every patch to learn from, so that it's able to learn the relationship between the patches. Then the feed-forward network, it processes the attended information to extract some abstract features from it. When it comes to the layer normalization and residential connections, this keeps the training stable to help with word flow during training. So all these layers all these layers, when all these layers are done, the token is passed into a final classification layer. So the output is a probability distribution over the 40 foods that are in the model, telling us what food is most likely to be in that image. So that the model is usually trained. The model was trained using cross interest loss and optimized using the ADAM, which balances learning and regionalization. You can put it in simple terms. The part embeddings, they let the model read the image. After the model read the image, the attention layers help the model think the relationship between the different patches of the between the different patches that are in the image. Then the classifier head lets us decide what food it is that we see. After training, we observe that the model's training accuracy increased steadily, but the validation accuracy dropped after some time, hence giving signs of overfitting. It means the model memorized some parts from the training data instead of learning to generalize from them. With this still, the VIT model showed clear learning behavior and correctly identified most common foods such as beans, matoke, and cassava. We trained the model on 782 images and validated it on 196 images. The results show that the model performs reasonably well considering the small data set. So, using augmentation, we're able to get more images and then we improve the accuracy of the model. These GAN-Augmented images balance the classes. For example, they added more cassava, yam samples to the dataset. We deployed our large language model, the fine-tuned one. So the model that we deployed, it was able to be like you could be able to search for recipes, as you can see in the interface. You search for recipes that you want, then it brings for you the recipe, everything about that particular type of food that you want to cook, and then the ingredients contained in that food. And then if you feel like that's not what you want, or you want to look for something else, you can search another food. There were, like we said, there were like 162 recipes, and then if you want to start cooking, you start cooking, then to bring for you steps on how to cook from step one to the very last step. And then there's a part where you can ask AI about that food or any other type of food and it will give you a response. So this was our first deployed model. So we're trying to further integrate the CV and the knowledge graph so that our product can improve and give us recommendations. And for now, we have just deployed the large language model with the recipes, and now we're going to integrate it with the images and the knowledge graph so that it can be fully a working system. So limitations first throughout our entire project. Some of the fields we have noted down are limited access of the Ugandan food resources. So we solve this by going around like our surrounding areas, that asking the local people, taking pictures of local foods, getting images of the internet of the local foods, looking through recipe books of Ugandan local dishes so that we can widen our data set. And then there was also language and cultural constraints while fine-tuning the element. This we solved this problem by integrating pre-trained local language models so that they can be able to learn, like especially like Uganda. It was like difficult at first, but then with integrating these pre-trained local language models, you could tell at the end of it like it's now picking on the local language. And then there was multi-step reasoning when you're using the RCGN. Then we solved this problem by implementing an automatic knowledge graph where it was constructing training from like websites and articles. So we managed to integrate the large language model and the CV and also the knowledge graphs. So we also used the GANs to make as I said, because in the beginning it was very small because of little data and like lack of a local Ugandan data set that we could work with that's large enough. And then we implemented a nutrition knowledge graph to provide personalized health awareness meal recommendations. In case you want a meal based on your health profile that you put into the model, it can be able to recommend food that is good or is coordinating with your health and is good for your health. And then we look forward to like integrating real-time market data to improve like on-season variability and pricing trends. So if in case like this is what is there on the market, this is the type of food that is, it's the season, the model can be able to tell that this is the time for this, so it's going to be in plenty. You can suggest what's here, like this time of this particular moment, this is not available, but you can use this as the time for this comes. And also we also look on expanding our large language model to support wider languages. Like for now we only train on Uganda, so we expect to expand to other languages in Uganda, Nyankole, Acholi, Ugisu, so that it can be used by everyone in Uganda in their own language, not just the central language. So the model focuses to work on the data expansion as we engage more in community and data connection. So the data that we have, as we collect more data about different languages, how they call these different foods, we expand our data and the images. We expect the model to work reasonably well. We'd like to acknowledge and thank Mr. Baliwangu Marvin for his support as he has pushed us through this project from the very beginning until where we are. So we really appreciate it and we don't take it for granted. Thank you so much for listening. Have a nice day.